This is Dr. B.S. Londe, and today we are going to see fourth part of the chapter Reagents in Organic Synthesis. Here, in this lecture, selenium dioxide is the reagent for our study. So, and out of all the uses of selenium dioxide, oxidation of carbonyl compounds and allylic oxidation, these are the two main uses or main functions that we are going to see today. So what is meant by carbonyl compounds? Compounds containing C double bond O group. These are carbonyl compounds. And allylic, the allylic position is if there is carbon-carbon double bond and from this carbon-carbon double bonds, this first carbon from either sides that is known as allylic carbon. And oxidation of this position will be known as allylic oxidation. So let us see the preparation of selenium dioxide. It is prepared directly by burning metallic selenium in air. This selenium burns with blue flame and get oxidized to dioxide. So this is metallic selenium. In presence of air, when it is burned or heat is provided, we get oxidized product, that is selenium dioxide. It is highly toxic white crystalline solid. It is soluble in dioxane, ethanol, acetic acid, and it dissolves in water to give selenious acid, H2SeO3. And this is the actual reagent working as or acting as oxidizing agent. Selenium dioxide is mainly used as oxidizing agent, but it is equally useful reagent for allylic hydroxylation and dehydrogenation reaction. Dehydrogenation, it is the removal of H2 from the reactant. The reaction are carried out in aqueous acetic acid or anhydrous medium at elevated temperature or near about 100 to 140 degrees Celsius. So first use as oxidizing agent in presence of small amount of sulfuric acid, that is H2SO4, selenium dioxide oxidizes internal alkynes to alpha diketones. So here the condition is internal alkynes. Internal means the carbon carbon triple bond is in between the molecule, in the structure of molecule. It is not terminal. Terminal means the carbon which is end carbon. This is terminal alkynes. But internal alkynes means there is extension of chains on both the side. These are known as internal alkynes. So internal alkynes are oxidized to alpha diketones. Here the specifically reaction center is this triple bond is converted into single bond, and here two carbonyl groups or carbonyl carbons have been generated. Diphenyl acetylene, when treated with selenium dioxide in presence of sulfuric acid, we get benzyl. Alpha diketones. Alpha 1,2 diketones are also known as alpha diketones. Adjacent diketones. Another example, phenyl acetylene. This is terminal alkyne, and this phenyl acetylene is also oxidized in presence of selenium dioxide and sulfuric acid to phenyl glyoxylic acid. Here same reaction happen. This triple bond is converted into single bond, and both the carbons have been converted into carbonyl group. The oxidative action of selenium dioxide SiO2 is especially targets at reactive methyl and methylene. This methylene means CH2 and methyl means CH3. So these are the two targets for oxidation. Selenium dioxide oxidizes this methylene and methyl in alpha position to carbonyl group or double bond. So I'll, if this is there is double bond in the reaction, this is the alpha position, or this is also known as allylic position. And if carbonyl group is there, then this is the alpha position. So these are the two susceptible positions, or they undergo the oxidation reaction in presence of selenium dioxide. Let us see some examples. Acetaldehyde, and this acetaldehyde under aqueous condition, dioxime is used as solvent. Selenium dioxide converts this acetaldehyde into glyoxal. What happened here? This is alpha position and it is oxidized to aldehyde group CHO. The structure of acetaldehyde is CH3 C double bond OH. It is, as this is alpha position, it is converted into C double bond O, and this H3 will remain as H. Here, next example is acetone is converted into methyl glyoxal. Here also there are two alpha positions, but when we use equivalent quantity of selenium dioxide, it converts this alpha carbon into aldehyde group. Similarly, acetophenone is converted into phenyl glyoxal and diethyl malonate is converted into diethyl mesoxalate. In cycloalkenes and cycloketones, the methylene group at alpha position to double bond is oxidized. Here, when we take the example of cyclohexene, this is alpha position and this is also alpha position. When selenium dioxide is 1 is to 1 in 1 is to 1 quantity is used, it oxidizes the alpha position. Any alpha position is oxidized and we get the carbonyl group at alpha position with respect to this double bond, and the product is 2 cyclohexene 1-ON. Cyclohexanone, when treated with selenium dioxide, it converts this alpha position into carbonyl and we get this, and this is product. Then selenium dioxide is also used as hydroxylating agent. Hydroxylation of allylic and benzylic compounds is achieved with the help of selenium dioxide. Primarily, selenium dioxide SiO2 hydroxylates methyl and methyl group at allylic or benzylic position. So, methylene that we have seen CH2 and methyl CH3. This is CH3. The preference order of oxidation, if CH2, CH3 and CH, all these groups, all these fragments are present, preferentially CH2 is oxidized first, then CH3, and after that CH is oxidized. The oxidation occurs at more substituted end of the double bond. So here, when we take the example of 2-methyl 2-butene, the carbon-carbon double bond, this side is less substituted and this side is more substituted. So CH3CH3, out of these two groups, any one can be oxidized and we get 2-methyl 2-butanol. This is the product. And in this second reaction, the 3-methyl 2-pentene selenium dioxide oxidizes. So here, this is the product, that is 3-methyl pent 3A-EN2OL. Here, as we see, these are the two sides of double bond. This is less substituted and this is more substituted. And here, one is CH3 and another alpha is CH2. So preferentially CH2 will be oxidized or hydroxylated, as this is the preference order. So CH2 is oxidized or hydroxylated and we get 3-methylpent 3-ENE2OL. Then dehydrogenation. At elevated temperature, it promotes oxidation by some dehydrogenation reaction. Benzyl alcohol undergoes dehydrogenation. This dehydrogenation means removal of H2 molecule. Here, this when we remove H2 molecule, we get benzaldehyde from this benzyl alcohol. Similarly, acetic acid upon dehydrogenation gives succinic acid, and ethyl succinate upon dehydrogenation gives ethyl fumarate. Thank you.